Hello everyone, welcome to pre-algebra. This lecture is going to be on section 2.2, so the second section of module 2, where basically I'm going to give you an introduction to fractions, so what fractions are in general, and then in the next two sections, 2.3 and 2.4, we will learn how to add and subtract and multiply and divide fractions, as well as mixed numbers too, which are related to fractions. Okay, so let me start by giving you a definition. So in general, sort of qualitatively, a fraction just means a part of the whole. So a fraction means a part of the whole. Okay, so that's sort of like a qualitative definition. A more exact definition is a fraction is any number that can be written in the form a over b where a and b are, we're going to stick just with no negatives right now, so I'll just say whole numbers. So where a and b are whole numbers, so whole numbers, and it's really important b can't be equal to 0, right? Because we know we can't divide by 0, otherwise that would be undefined. So I'll say and b is not equal to 0. So a fraction is any number that can be written in the form a over b, so as that ratio a over b, where a and b are whole numbers and b is not equal to 0. Now the a has a name, it's called the numerator. So this is the numerator. And the b is the denominator. Okay, so numerator, denominator. All right, now pictorially, we can represent fractions as like a shaded figure, like part of a shaded figure. So for instance, let's say I want to know what fraction does the following figure represent. So what fraction does the following figure represent? Okay, so here's the figure. Let's say it's a rectangle. Let's say I split it up into 8 identical little rectangles. And let me shade, I'll do this in blue, let me shade this part right here. Okay, so the way to think about this, right, you can think of the whole thing as one whole, right? So there's 8 pieces, and I'm shading 3 out of the 8, right? So the fraction that represents that picture is going to be 3/8. So this really represents 3/8, right? So 3 pieces are shaded out of the 8, right? 3/8. Here's another example. Let's say I have like a circle here, and let's say this part is shaded. So what fraction does that represent? Well, the whole thing is a circle, right? And I have it broken up into 4 pieces, and one of those 4 pieces is shaded. So this fraction is going to be 1/4. fourth, right? 1 out of 4 parts is shaded. Okay, a little bit with terminology. If I have a fraction where the numerator is less than the denominator, that's called a proper fraction. So let me just give you an example. Let's say 7/10, right? That would be an example of a proper fraction. Where the numerator is less than the denominator. If the numerator is larger than or equal to the denominator, that's called an improper fraction. So let's say, like 12/5 is an example of an improper fraction. And what makes it improper is the fact that the numerator is greater than. I think you could also say greater than or equal to the denominator. So the numerator is greater than or equal to the denominator. All right, so that would be improper. Now it turns out that an improper fraction can also be expressed as a mixed number. So in this case, the 12/5, right, could also be expressed as the mixed number 2 2/5. And notice that the mixed number has a whole number part and a fraction part. So I'll say which has a whole number part and a fraction part. Okay, so what does that mean? When I write 2 2/5, this means 2 plus 2/5. Okay, it's just a more efficient way of writing 2 plus 2/5. In pictures, it would be something like this. Like, let's say I'll use rectangles again. So these are all the same size, right? And this one I'll split up into 5 pieces. And I'm going to shade these complete ones, so these 2 holes. And then this one I'll shade just 2 out of the 5 parts. Okay, so this is just a pictorial way of representing 2 2/5. Okay, and notice here that this is equal to, if I were to break all of them up into 5 pieces, let me draw this here. Okay, and then again, shade it. So again, this whole thing is shaded. And then this is 2 of them. And you look at all the shaded pieces. Now that I broke everything up to 5, how many of those? Well, I have 12, right? And then it's always out of one whole, which is 5, right? So this is going to be, this is another way of saying this equals 12 fifths. Okay, so those are identical. 12 fifths is an improper fraction, but you can write it as a mixed number, 2 and 2 fifths, and you can go back and forth between these. We'll learn how to do that. Actually, we'll learn how to do that next. All right, so how do I convert a mixed number to an improper fraction? Let's do that first. So converting a mixed number to an improper fraction. Okay, so if I want to convert (1 1/3) to an improper fraction, let's say that's our example. All right, so how do I do that? Let me just give you the rules here. You could do this by addition, but we haven't really talked about adding fractions yet. So let me give you the rules, the quick way of doing this. So what you want to do first is you want to multiply the denominator by the whole number part. So multiply the denominator by the whole number part. So in this case, that would be 3 times 1, right, is equal to 3. So that's the first step. I multiply the denominator of the fraction part by the whole number part. Then I add this to the numerator of the fraction part. So add the value I'll say from step 1 to the numerator, okay, of the fraction, meaning of the fraction part. Okay, so this would be, I have the 3 now, I have to add that to the 1, right? That's numerator of the fraction part, to give me 4. And then I write that sum over the original denominator. Right, the sum from step 2 over the original denominator. So then this would be 4 over the original denominator, which is 3. And then I'm done, right? So I converted a mixed number, or mixed numeral, into an improper fraction. So it just equals 4/3. Okay, let's do some examples of this. So let's say I have 6 and 5/6. I want to convert that to an improper fraction. So I need to multiply, right, 6 times 6. Remember, it's a fraction part times the whole number part. It's a denominator times the whole number part. So that's 6 times 6. Plus, I add the numerator and then put the whole thing over the original denominator. Okay, so this will be 36 plus 5 over 6, which is the same thing as 41 over 6. Okay, here's another example. Let's say I have 2 and 7/13, right? So that's my mixed number. I want to write it as an improper fraction. So I multiply the denominator by the whole number part, add that to the numerator, and put the whole thing over the original denominator. So this will be 26 plus 7 over 13. And then 26 plus 7 is what? 33 over 13. So 2 and 2/7 is equivalent to 33/13. Okay, what about going the other way? Let's say I want to convert an improper fraction to a mixed number. So converting an improper fraction to a mixed number. Okay, how do I do that? Basically, you just divide, and then you put, so you're going to end up with the quotient, which is the whole number part, and then you put the remainder over the denominator. Okay, so I'll say the rule here is just divide keep the whole number part and put the remainder over the original denominator. Okay, so the whole number part is basically going to be the quotient, right? And then you're going to take the remainder and put that over the original denominator. So here's an example. Let's say I have, let's say I want to convert 31 halves to a mixed number. Okay, so I'm going to divide this. So 31, I'll just do long division, divided by 2. So 2 goes into 3 once, right? 1 times 2 is 2. I subtract, bring down the next one. 2 goes in 11 5 times. I multiply 5 times 2 is 10. And now I subtract, and my remainder is 1. So as a mixed number, it's going to be 15, right? So that's going to be my whole number piece. And then I take the remainder, which is the 1 here, and I put that over the original denominator, which is the 2. So this will be 15 and 1 half. That would be that same number converted to a mixed number. Okay, let's do a few more examples of this. Let's say I start with 41 over 8. I want to convert it into a mixed number. So I'm just going to divide this out. 8 goes into 4, doesn't 41, and goes in 5 times. Right, so this will be 40. My remainder is going to be 1 when I subtract. So 41/8 is the same as 5 and 1/8. Okay, and then let's say you get something that goes in evenly, right? So if you have 72/9, let's say. So try to convert this into a mixed number. When I divide this, I'm going to find, oh, that goes in exactly, right? It goes in exactly 8 times. The remainder is 0. So then my answer is just going to be 8. There is no fraction piece, right? It happens to be, the answer happens to be a whole number, right? There's no fraction piece. Okay, so that could happen. You don't always have to have a fraction piece. You could say, it's 8 and 0/9, but you would never write the 0/9. You would just say it's 8, and that would be it. Okay, another important concept is something called equivalent fractions. So equivalent fractions. So what does it mean to be an equivalent fraction? It really means that in essence the fractions are the same. They represent the same piece, right? So here's an example. Let's say I want to draw 3 rectangles again. They're all going to be the same size. This one I'll split just into halves. This one I'll split into quarters, like 4 pieces. And this one I'll split into 8 pieces. Okay, so here I'm going to shade this. Here I'll shade this. Here I'll shade this. Okay, now if we represent each of these as fractions, right? The first one, well, I have one rectangle shaded out of 2, right? Because I split it into 2 pieces. So this represents 1/2. The second one, I have 2 shaded out of 4, so this represents 2/4. And the third, I have 4 shaded out of 8, so this is 4/8. But notice, if you look at this, really these are all the same, right? Because it's really the same amount that's shaded out of the whole. So really these are equal to one another. So that's what we mean by equivalent fractions. These fractions are really the same. They're just written with different denominators is another way of saying it, right? They're expressed differently, but they really represent the same thing. They all in some essence mean 1/2. Okay, let's say I want to write I'll give you a proper fraction, say 4/9, as an equivalent fraction, but given a particular denominator. So let's say write 4/9 as an equivalent fraction whose denominator is, let's say, 63. Okay, so I start with 4/9. I want to end up with another fraction which is equivalent. So in some sense, it's really the same fraction. But instead of having 9 as the denominator, I want 63 as my denominator. All right, so how do we do this? Well, ask yourself, just look at the denominator right now. 9 times what will give me 63? Well, we know 9 times 7, right? So I need a 7 down here to get to 63. But because I'm not changing the fraction, I'm just rewriting it in a different form. It has to be equivalent. That means I have to multiply by 1, right? This has to be equal to 1. Because whenever you multiply by 1, you don't change something. You might rewrite it in a different form, but it's still, in essence, the same thing. So how can I make that equal to 1? Well, if the denominator is going to be 7, the numerator also has to be the same thing, right? So it also has to be 7. And then we haven't talked about multiplication yet, but basically you multiply across the numerator. So 4 times 7 is 28. So 28 over 63 would be equivalent to 4/9. Okay, here's another example. Write 5 as an equivalent fraction whose denominator is 15. Okay, so again, I'm going to start with 5. And really, if I want to represent this as a fraction, let me put 5 over 1, right? So you can, a whole number can be represented as a fraction if you put it over 1, right? That's always possible. But I want my answer to represent the same thing. I also want it to be equal to 5 in some sense, but I want my new denominator to be 15. Okay? So again, how do I get 15 in that denominator? Well, I already have a 1 here, so what do I need to multiply by to get 15? Well, I need a 15. But since this has to be a factor of 1, I also need a 15 in the numerator, right? Whatever I have to multiply by in the denominator, that also has to go in the numerator. And now I can multiply across the numerators, 5 times 15, and that's going to be 75. So 75/15 is the same as 5, right? Or 5 over 1. All right. How do we determine if two fractions are equivalent? So let's say we want to determine if 2/7 equals, I'll put a question mark here, 10/35. So in other words, the question I'm asking is, are 2/7 and 10/35 equivalent? If they're equal, then they're equivalent fractions. There's several ways you could do this, right? We could try to simplify, and we'll talk about that in a little bit, how to simplify fractions to see if we can get one side to look like the other side. Or you might say, well, over here, if I multiply by 5 over 5, I can get this so it has the same denominator. And actually, I'm going to get 10/35, so it looks like that they are equivalent. They are going to be equal. But the quick way of doing this, of checking whether two fractions are equal or not, is by cross-multiplying. So let me show you that way, the quick way. Again, there's several ways you can do it, but let's use cross-multiplication. So I'll say use cross-multiplication. So what you're going to do, let me set these up again. And again, we're not sure if that's equal, so I'll put a question mark here. You're going to multiply upper left by bottom right. I'll write that on the left-hand side, so 2 times 35. And then I'm going to multiply bottom left times upper right. So 7 times 10. So again, upper left times bottom right. And then on the right-hand side, I'm multiplying bottom left times upper right. And if I get the same answer, which in this case I get 70, if they're equal, right, if those are equal, then the original fractions are equal. They're equivalent. So in this case, it's yes. So 2/7 equals 10/35. Yes, they are equivalent. They're equal. And again, I checked it by cross multiplication. Okay. The other way you could do it is, again, you could try and rewrite one fraction in terms of the other. If they have, you could write the 2/7, right? So it has a 35 in the denominator, and then if the numerator matches, then obviously it's equal. Okay, what about simplifying fractions? Often we want, especially in my open math, sometimes they will want the answer in simplest form. So how do we simplify fractions? Okay, so I want to write, so I'll say writing a fraction in simplest form. Okay, so for example, let's say I want to simplify 9/12. Okay. Again, there's several ways you could do this. One way is seeing if there's common factors in both the numerator and denominator. Because if there's common factors, you can cancel them out. Really what you're doing is you're removing a factor of 1. Okay? So we could think of this as, I'll show you a more general way that will always work, but for now, usually what you do is say, okay, does something go into 9 and 12? Yeah, it looks like 3 does, right? In other words, I can think of 9 as 3 times 3, and I can think of 12 as 4 times 3. So this 3 over 3, this is a factor of 1, right? 3 over 3 is 1. So I can remove it. Usually what we do is we say we cancel out 3's. And then we end up with 3/4. And there's nothing else I can remove, so that would be the fraction in simplest form. Okay? If I have, say, let's say I have 30 over 18. So you might think, okay, what goes into 30? What goes into 18? It looks like maybe 6, right? So 30 could be written as 5 times 6, and then 18 is 3 times 6. I can cancel out the 6's now, right? Because I'm removing that factor of 1, and I'm left with 5/3. Okay? Or if you wanted to write it as a mixed number, it'd be 1, right? Remember, you divide it, and then the remainder is 2 over 3. So 1 2/3. All right, what's another way you could do this, like, that will always work, a more general method? Let's say you can't easily think of a factor that goes into both of them. Well, we could use prime factorization again. So that prime factorization is really, really useful. So let's say I want to simplify, and actually I would suggest you do it this way if you have very large numbers. So let's say 36, I'll still stay pretty moderate with the numbers, but if you have very large numbers, this is probably the way to do it. Okay, so what do? We factor both of those numbers into a product of prime numbers. In other words, we find the prime factorization of both numbers. So we do the tree, right, on the numerator and the denominator. So remember how to do this, right? I start with, remember the prime numbers are 2, 3, 5, 7, and so on. I start with the lowest prime number, 2. Does that go in? Yep, it goes in evenly 18 times. Then I branch off the 18. Does 2 go into 18? Yes, it goes in 9 times. Does 2 go into 9? No, but then I work my way up to the 3. Does 3 go in? Yes, it goes in 3 times. And then I stop because I have all prime numbers, right? So 36 is the same as 2 times 2 times 3 times 3. Or you could write it as 2 squared times 3 squared. And in 45, again, start with the 2. Doesn't work. The 3, yes, that goes in 15 times. Then I branch off to 15. Does 3 go into 15? Yes, it goes in 5 times. And then I can stop because these are all prime numbers, right? So it's going to be 3 times 3 times 5. Or I could write as 3 squared times 5. So this 36 over 45 is really the same as, so the numerator here I can write, remember 36 is 2 times 2 times 3 times 3. And then 45 is 3 times 3 times 5. And then it's easy to see what factors of 1 you can remove, right? What cancels. 3 cancels with a 3. This 3 cancels that 3. That's it. So what do I have left over? Well, in the numerator, I still have 2 times 2, which is 4. And in the denominator, I just have a 5. So this really simplifies to 4/5, okay? So really what happened here was I took out a factor of 9 over 9, but you may not have seen that 9 went into both 36 and 45. If you see that, that's a quick way of doing it. But if you don't, then you can always use prime factorization, and this will always work. Okay, what about comparing fractions? Like seeing which one is greater, which one's smaller. How do we compare fractions? Let's talk a little bit about that. So comparing fractions. Okay, so first thing, before I get into comparing fractions, a little bit of terminology. Like fractions are defined to be fractions with the same denominator. So these are just fractions with the same denominator. And then unlike fractions as you can guess, are fractions with different denominators. So these are fractions with different denominators. Okay, so how do I compare fractions? Well, it depends whether they're like or unlike, right? So let me write out the rules here. So to compare fractions, so first, if the fractions are like, right, if they're like fractions, all we have to do is compare the numerators. So if the fractions are like, just compare numerators. If the fractions are unlike, write them as equivalent fractions with the same denominator, then compare numerators. Okay, so if the fractions are unlike fractions, I'll just say unlike, then you write them as equivalent fractions with the same denominator. And actually, usually you use what's called the lowest common denominator. So I'll say usually you use the lowest common denominator. Which is also called the LCD. And then once they're written with the same denominator, then you just have to compare numerators again, because now they're sort of like fractions, right? Then I'll say then compare numerators. Okay, and so one thing I should mention, right? We haven't really talked about lowest common denominator, but we sort of have, because it's simply the lowest common multiple, which we have talked about, of the denominators. So let me mention it here. So the lowest common denominator or least common denominator so least common denominator, the LCD, is the lowest common multiple, remember we talked a lot about that LCM, of the denominators. Right, so the lowest common multiple you would just find of, normally we have two numbers, right? In this case, the two numbers will be the two denominators of the fractions. Okay, so let's do some examples with this, comparing fractions. Let's say I want to compare. I'll start with an easy one. So let's say I want to insert the correct inequality symbol. And what I mean by that is either less than or greater than. So either that means less than, greater than. And this is greater than. Okay, so here's the question. I have 5/10, and I'm going to compare that to 3/10. All right, so the nice thing here is notice immediately that both these fractions have the same denominator, right? So they're like fractions. So all I need to do is compare numerators. So how does 5 compare with 3? Well, 5 is greater than 3, right? We know that 5 is greater than 3. Therefore, 5/10 must be greater than 3/10. So if they already have the same denominator, all you have to do is compare numerators, and that answer will be correct for the fractions themselves. Okay, so that's the easy case, right? If they're like fractions. What if they're not? Let's say I have this. Again, I want to compare, say, 5/6 to 7/8. Okay, so what I want to do is rewrite these so that they're equivalent fractions with the same denominator. So let's find the lowest common denominator. So remember, the lowest common denominator, or least, some people use least, some people use lowest, is the least common multiple or lowest common multiple of the denominators of 6 and 8. So you have to go back to what we learned, right, in the previous section. How do I find the lowest common multiple of 6 and 8? Well, you could do this mentally, right? You could say, okay, what's the smallest number that 6 and 8 will go into evenly? And you might come up with 24, right, which is the correct answer. The other way of doing this is, remember, we can do it by finding the prime factorization of each. So this method will always work. So what's the prime factorization of 6? Well, 2 goes into 6 3 times, and then they're both prime, so I can stop. And then 8 is going to be 2 times 4, 2 times 2, right? So I have to do the tree for both of them. And remember, to find the lowest common multiple, which in this case is going to be lowest common denominator, is I look at each factor and I take each factor the greatest number of times it occurs in either of the factorizations. So the 2 occurs once in this factorization. It occurs 3 times in this factorization. So I need to take the 2 3 times. All right, and I multiply it all. I form a product, so I multiply everything together. Then I look at the other factor, 3. The 3 occurs once in this factorization, 0 times in this factorization. So the greatest number of times that it occurs in either of these is once. So I need to take the 3 once. So again, I multiply by 3. And if you do this out, 2 times 2 is 4, times 2 is 8, times 3 is 24. So 24 is our lowest common denominator, right? It's the lowest common multiple of 6 and 8. So I need to rewrite both of these fractions as equivalent fractions with 24 as my denominator. Okay, so in the first one, 5/6, right? What am I missing? Well, 6 times what? Just look at the denominator here. 6 times what will give me 24? I'm missing a 4, but I better put a 4 also in the numerator, right? Because it has to be a factor of 1. And now if I multiply the numerators together, 5 times 4 is 20. In the second one, what am I missing? 8 times what gives me 24? Well, it looks like it's 3. So I better put a 3 also in the numerator. And then 7 times 3 is 21. So this problem, this original problem of 5/6 compared to 7/8, is the same as 20 24ths compared to 21 24ths, right? They're equivalent. Remember, the original was 5/6 compared to 7/8, but I rewrote both fractions as equivalent fractions, and they both now have the same denominator. So now these are like fractions, right? So I just have to compare the numerators. So how does 20 compare to 21? Well, it's less than, right? 20 is less than 21. Therefore, 20 24ths must be less than 21 24ths. But because 20 24ths is the same as 5 6 and 21 24ths is 7 8, then that means 5 6 is less than 7 8. Okay, what if you have a mixed number? Well, often what you do is you just convert it to an improper fraction, right? And then you can continue the work. Let's say we have 2 3/7, and I want to compare that to 2 and, I don't know, let's say 5/14. Okay, well, because the whole number parts are the same, we could actually just compare the fraction pieces, but it's easier just to convert these into improper fractions, right? So remember 2 3/7. How do I convert that to an improper fraction? Well, I multiply 7 times 2, right? The denominator times the whole number part, plus I add that to the numerator, plus 3, and I put it over the original denominator. So this is going to be really 14 plus 3, which is what, 17 over 7. And then the other one I have 2 5/14. So this is going to be 14 times 2 plus 5 all over 14, right? So this is going to be what, 28. So plus 5 is 33 over 14. So really this problem becomes, I'm comparing 17/7 to 33/14. Okay, but I can't compare those directly because I don't have the same denominator, right? So I can rewrite them so that they're rewritten both with the lowest common denominator, right? So I'm finding equivalent fractions for both of them where I'm going to use the lowest common denominator. Well, you might think here, what's the smallest number? Instead of doing that, let's just think about this. What's the smallest number that both 7 and 14 will go into evenly? Well, it must be 14, right? 7 goes into 14 twice, 14 goes into 14 once. So 14 is our LCD. So this one, I don't need to do anything to. It's okay. It's already written as something over 14. The other one, I can rewrite this, right? Remember, I want a 14 down here. So to fix it, I need to multiply by 2, right? 7 times 2 gives me 14, but I also need a 2 in the numerator. And then 17 times 2 is 34. So this problem really becomes now 34/14 compared to 33/14. And now that they're like fractions, right, they have the same denominator, 14, it's easy to compare. We just compare numerators. And obviously 34 is greater than 33. So the original answer was 17/7 is greater than 33/14. And actually, if we go back to the original problem, we had it written as mixed numbers. I guess 2 3/7 is greater than 2 5/14. Okay, so the whole goal here is to rewrite them so that they have the same denominator. Usually use the lowest common denominator. Then all you have to do is compare numerators. Okay, let's look at an applied problem here. So this says, in a course on probability and statistics, a student learns that when rolling a pair of dice, the probability of getting a 5 is 1/9, and the probability of getting a 6 is 5/36. Does getting a 5 or 6 have a greater probability? Okay, so really what we want to do here is we want to compare those two fractions, right? We want to compare 1/9, all right, the same way we did before, to 5/36. And whichever one's greater, then that's going to be the larger probability, right? So how do we compare these? Well, they don't have the same denominator. We want to rewrite them so they have the same denominator. So we want to typically use the lowest common denominator. So the lowest common denominator in this case is the smallest number, the lowest number that both 9 and 36 will go into evenly. So again, mentally you might be able to figure out, well, That must be 36, right? Because we know 9 goes into 36 4 times, and 36 goes into 36 once. So 36 is the LCD. If you don't see that, then you can always go to prime factorization, and you can work it out, right, that way, and that will give you the answer, and we will get exactly 36. So the 536 is okay. The 1/9 I need to rewrite. I want to write it as an equivalent fraction with 36 as my new denominator. So what am I missing here? Well, 9 times 4, right, will give me 36. So I also need a 4 in the numerator. And then 1 times 4 is 4. So really this problem now becomes comparing 436, because that's equivalent to 1/9, to 536. Well, once we have the same denominator, right, they're like fractions, so I just have to compare numerators, and it's clear that 4 is less than 5, right, when I compare numerators. Therefore, 1/9 was less than 536. So 536 is really the greater number, right? So that means that there's a greater probability that I roll a 6 than a 5, right? Because a 6, when I'm rolling 2 dice, has a probability of 536, where rolling a 5 only has a probability of 1/9. Since 536 is greater than 1/9, there's a greater probability of rolling a 6. So the conclusion here is there is a greater probability of rolling a 6, right? Because 536 is larger than 1/9. Okay, and then let me just finish up this lecture by looking at a couple of example problems from my Open Math. So this problem right here, I would just want to simplify that fraction, right? 105 over 135. It may not be obvious like what goes into both of those numbers. So one thing we could do is we could find the prime factorization, right, of both numbers. And then we know that we'll get this to work. So let's do it that way. And then I'll show you another way that you can think about this. You can maybe do it quicker, but let's find the prime factorization. So again, I always start with the lowest. Remember, the prime numbers are 2, 3, 5, 7, and so on. 2, does it go into 105? No. Does 3 go in? Yes, because the sum of the digits, 1 plus 0 plus 5 is 6, and 3 goes into 6, so it must go into this. So 3 goes in, and you might have to go to the side to figure out how many times, like divide it. So it goes in, this is going to be what, 35 times? So this is 35. Now I branch out to 35. Does 3 go into 35? No. Does 5 go in? Yes. 5 goes in 7 times. Okay, and then we're done. So 105, its prime factorization is 3 times 5 times 7. Now I go to the 135. Does 2 go into 135? No. Does 3? Well, 1 plus 3 plus 5 is 9. 3 goes in 9, so it must go into 135. How many times? Well, let's figure it out. So this would be what? 4. And I bring down to 5. And then 3 into 15 is 5. So I guess it's 45 times. Then I branch off to 45. Does 3 go into 45? Yes. It goes in 15 times. Does 3 go into 15? Yes. It goes in 5 times. Okay, so that original problem now, right, I can write, instead of 105 over 135, I can write this 105 is 3 times 5 times 7. And then 135 is 3 times 3 times 3 times 5. Now it's easy, right, to simplify this. I just cancel out factors of 1, right? So I have a 3 here, that cancels out with 1, 3. That's a factor of 1. I have, let's say, a 5, that cancels with that 5. So it turned out I took out a factor of 15 over 15, right? It wasn't obvious that 15 went into both those numbers. So what am I left with? Well, I'm left with 7 in the numerator, and then 3 times 3 is 9 in the denominator. Okay, Now, be careful. If you cancel everything, you can't say that you're left with nothing, right? In the numerator, there will always be a 1 there, right? Here, actually, let me do an example just to make sure that... Here, I'll take a simple example. Let's say I want to simplify... let's say 10 over 100. Okay. Now, this one is not bad, right? We can do it, but let's work it out by finding the prime factorization. So this would be 2 times 5, right? And then this one would be 2 times 50. Then I branch out to 50, 2 times 25, and then 5 times 5. So 10 over 100 is the same as 2 times 5 over 2 times 2 times 5 times 5. So then you might say, okay, I can cancel out the 2's, I cancel out the 5's. Wait, I don't have anything left, but you do. Remember, that there's always a 1 there, right? 10, I can write 10 as 2 times 5 times 1. There's always a 1 there, so you have to remember there's a 1 there. And then my final result now will be 1, and the denominator I have 2 times 5, so that's 1/10. So 10 over 100 simplifies to 1/10. Okay? Okay, so question 5, this question. They give you 3 fractions, and all I want you to do is find the least common denominator of 15, 21, and 12. But remember, right, the least common denominator is going to be the least common multiple of those numbers, of 15, 21, and 12. Okay, so how do I find the least common multiple of those numbers? You might be able to do it just mentally, right, in your head. If not, then we have to factor each number first. I can find the prime factorization. So 15 is 3 times 5, and I can stop because they're both prime numbers. 21 is going to be 3 times 7, and 12 is going to be 2 times 6, and then 2 times 3. Okay, so this is 3 times 5, 3 times 7, 2 times 2 times 3. Then remember, to find the lowest common multiple, which ultimately is going to be our lowest common denominator, I need to take each factor the greatest number of times it appears, right? It occurs in either of the factorizations. So I have 2's, 3's, 5's, and 7's. So let's start with the 2's. How many times does 2 occur in this factorization? 0, right? How many times does 2 occur in this factorization? 0. How many times does 2 occur in this factorization? 2 times. So I need to take the 2 twice, and then multiply. I'm forming a product. Now let's go to 3, I guess. How many times does 3 occur in this factorization? Once. Here, once. Here, once. So the greatest number of times in either of these is just once, right? It's like a tie. So I take the 3 once. Then I go to 5. How many times does 5 occur in this factorization? Once, 0, 0. So the greatest number of times is once. And then finally, 7 is my other factor, right? 7 doesn't occur here, so 0, 1 versus 0. So the greatest number of times is 1. So I take the 7 once. And then if I multiply all those numbers out, that's going to be my least common multiple of those numbers, which in this case is our least common denominator, because all those numbers were in the denominator. So what is this? Let's say this is going to be 4 times 3, right? So I'll do it left to right. This is 4. This is going to be 12, right? Times 5 times 7. And then 12 times 5 is 60. And then I guess 60 times 7 will be what? 420. So it looks like that's going to be my lowest common denominator, 420. So if I wanted to like add these or compare them, I'd have to rewrite each of them so that there's something over, each of them was something over 420. All right, great. So that's it for this section. The next section, which is 2.3, we will start talking about adding and subtracting fractions. Thank you.